Morning, everyone. I'm Carl. I work as an architect at NVIDIA, focused primarily on low-precision representations of numbers, largely for training, although a little bit for inference, which we'll be talking about later today. So if you want to hear more about small numbers after this, just stick around for another hour and a half. So what I'm going to talk about first is mixed precision training for neural networks. I guess just as a warning, this was originally a 45-minute pretty technical talk. We're going to do this in less than 25 minutes, so we're going to skip a bunch. And I'm going to move pretty fast. So if you have questions, I think there's a break at 10. Is that right? Mm-hmm. Yeah, break at 10. So come grab me and we can talk more about it because we're going to move here. So 3 things we're going to cover. The first is just going to be some background information. What is mixed precision training with FP16 and why this is a thing that you might want, why I think this is a good thing. Second, I'm going to talk a little bit about the methodology for doing mixed precision training. In order to get that goodness, there's certain steps that you have to take, and I'm going to walk through that at just a bit of a technical level. And then at the end, I'll talk about mixed precision training in practice, moving up from the algorithmic and mathematical level, talk about as a practitioner, as someone using software, how are you going to make this work? So what is mixed precision training? Just for a bit of background, we've mentioned tensor cores a bunch, so I'm just going to fly right through this. This is a hardware feature introduced first on Volta for accelerated matrix multiplies, which are used both for matrix multiplication and convolutions. It takes as input FP16 values and accumulates into FP32 in order to maintain precision, which is particularly important for training, actually, that you maintain high precision of your gradients. It has a throughput of up to 8x as fast as FP32, which is, pretty nice. And it's used by Cudianen and Kublas, as Ujjwal was telling us, in order to accelerate matrix multiplies and convolutions. It's also exposed in CUDA through the WMMA API, which I won't speak about, but if you want to actually program the tensor cores directly, that is possible. So in a nutshell, what is mixed precision training? It's kind of a game, and the game is that we want to keep all of the stored values that we have. So on the forward pass, that's going to be your weights and your activations, and on the backward pass, that's going to be the weight gradients and the activation gradients. We want to keep all of those in FP16 so that we can use the tensor cores to accelerate math and also maintain accuracy with that FP32 accumulation. That's it. That's all we're doing. And if you do this right, the benefits are up to 8x speedups for your math. And then also you have some big memory benefits. Now all of your numbers are just half as big as they were before. So you have half the storage requirements and half the memory traffic. The fun thing with the storage requirements actually is it often enables you to increase your batch size for a fixed memory budget, which can sometimes put you in a new regime in terms of performance by increasing the level of data parallelism. So you can actually see kind of super linear benefits there because of the decreased memory usage. So what does this look like? I'm just going to show a couple quick examples here. The first one here is using a library that's called Automatic Mixed Precision as a PyTorch library. The thing you're supposed to take away from this is that I changed 4 lines of code in the official PyTorch ResNet 50 training script that's available on the internet. Didn't change any hyperparameters, didn't touch anything else, and ran it on a V100, and things go faster. So this is actually a kind of old graph from August, so I actually expect it to look a little bit better right now. But there are 2 things you're supposed to take away from this picture. The orange line is the training curves, both train accuracy and train loss and validation accuracy, trained using mixed precision. Blue is FP32. 2 things I want everyone to take away. 1, the orange line is shorter. It's actually 2.3 times shorter, which is your time that you're getting back because everything is running faster. The other thing, and I'm just going to imagine, sort of use your head here to do a transformation of that orange line and stretch it back out by having the x-axis be in terms of iteration count rather than in terms of wall clock time. And you can imagine that these 2 lines will actually map exactly on top of each other, that there's not. One thing I've heard people say is there's a precision speed trade-off using mixed precision. There's certainly a precision trade-off insofar as FP16 has fewer bits, but there's not an accuracy trade-off in the machine learning sense of it. You're getting the same answers, you're getting the same results, it's just running quite a lot faster. As I mentioned here, the speed up depends a lot on the framework. There's a lot of software level stuff in order to make this work, which is what Ujjwal was talking about. I actually expect these numbers would be a little bit more now. These were, like I said, from some August builds of things. And there's work, at least for ResNet 50 in particular, to bring it above 3x everywhere. That's not just for ResNet 50, though. That's kind of building the underlying libraries. And when you add it all together, that's what you get for this particular model. this also works at scale. So this is actually just showing off some 8 GPU runs, which I don't think we really consider at scale anymore, but it's certainly more scale than you're used to. And so the nice thing about these FP16 speedups is they compose very nicely with all of the other things that we're doing to accelerate our software. So, this is MXNet, which you get about a 3x speed up on a single GPU, and it scales pretty linearly, at least up to 8 GPUs. And so when you add that all together, you get a total runtime of well under 4 hours on 8 GPUs for ResNet 50, which is pretty cool. So another thing I hope people take away is that mixed precision training is like a general purpose thing. It's not just for ResNet 50. It's also not just for like particular kinds of models or particular models that have certain characteristics. I've listed a whole bunch of models here. If you have a particular application domain you care about, come and bug me after. I'm not going to walk through all of these. But what you're supposed to do is be impressed by all of the number of things that I have up on this slide and say, wow, that's really a lot of kinds of models you guys have trained, and they all work. And by work, what I mean is that you both see acceleration using the tensor cores, but you also match the accuracy both at train time and at validation time as you did training in FP32. Here's some actual speed up numbers. I'm not going to walk through all of them. Again, what I'm hoping that people take away from this slide is, one, the application in the sort of different model sense of mixed precision training is pretty broad. We have, I think, mostly text and speech models up here. And then also, there's almost always some speed up. You see numbers here from 2.3 up to almost 5x. It depends a lot on the characteristics of the model because those tensor cores are going to be accelerating the math portion much more than they're accelerating memory-bound operations. And so when you add all of that together and the really deep software stacks, the numbers, it's a little hard to predict. And as Ujjwal mentioned, I think there's a lot of ongoing work to make this even better. So I bet these numbers are better than they were when I took them. And then the last kind of high-level point I want everyone to take away is that everything I've showed so far is take an existing model architecture that has, a known design, a known set of hyperparameters, a known training schedule, a known data set, and a known goal outputs, the thing that you're expecting to get at the end. And that's a really great application for mixed precision. There's another great application for mixed precision, which is doing novel research that, in a former life, I trained speech models for a living, and you spend a lot of time sitting around waiting for stuff to happen because it takes a while and you want to run experiments. And certainly if you can go buy more GPUs and then you can run more experiments in parallel, but actually having things get shorter, having that kind of literal speed up, being able to run, if anyone's had a job training neural networks, going from taking more than a day to taking less than a day is such a win because you can do 2 things in a day rather than 1. It's just the best. And so I've highlighted 2 instances here, one from NVIDIA, one from Facebook. These are links to archive papers. The first was language modeling work. The second was neural machine translation work, where they had relative speed ups of 4.2 and 5x, switching from FP32 to mixed precision. And those were numbers they measured after the fact, right? They did all of the work to do the research in FP16 because, at least having talked to both the Facebook and these NVIDIA guys who sit very close to me, they couldn't have done this without mixed precision, right? If everything had taken 4 times as long, they wouldn't have been able to, both improve the data sets, do all the hyperparameter tuning, do all of the various, sometimes it feels a little bit like drudgery, but all of the actual work of training neural networks to make this stuff work and not blow up or not fail to converge or not whatever it is. So I'd encourage everyone who does this for a living to check out mixed precision training. Great. That's my sales pitch part. Now we're going to talk a little bit about math and algorithms. So I've told you the story so far, which is that training with FP16 is a general purpose tool, not only limited to a particular set of applications. And the goal is to train with no architecture changes, no hyperparameter changes, nothing. You just take your existing model, you run it in FP16, and everything is great. Now FP16, you could have guessed this, only has 16 bits. Only have about 65,000 representable values. That's not that many numbers. Most numbers are bigger than 65,000, I would say. And so in order to get things to work, you do have some considerations, and there is a methodology in order to make mixed precision work. I've listed 3 parts here. It's more like 2.5, where the First part, model conversion, is about how do you actually take your thing and switch it over to FP16. And then the second two are kind of coupled, which is master weights and loss scaling, which have to do with how you compute the gradients and then use the gradients in order to update your weights. I'm going to walk through this pretty quickly, but maybe we'll have time at the end and you guys can ask a question. Kind of doubt it. So model conversion. This is a dumb slide. This is saying that for most of the model, what you do is you take it from FP32 and you switch it to FP16. So you have some weights, you have some layers. It depends a lot on the framework. So go look at your framework documentation. But you have some type somewhere. You want to switch that type to FP16. That's all this slide is saying. The more important point is that not everything is a matrix multiply or convolution. Certainly life in hardware land would be great if all you ever wanted to do was a matrix multiply. I encourage everyone who does research to only use matrix multiplies in your new models. Make my life a lot easier. But that's not true, right? There are a lot of things like activation functions, normalization functions, loss functions, and then miscellaneous weird stuff like in attention modules. Often you have kind of complex exponentiation, logarithms, dot products, reductions, things like that. And these are not going to run on tensor cores, right? Tensor cores are hardware support for accelerating matrix multiplying convolution. There you have that benefit of the intermediate FP32 reduction in order to maintain accuracy and precision. We don't have that for these pointwise or other operations, which are often just custom CUDA kernels, either built into the framework, built into cuDNN, built into cuBLAS. So I have kind of a more detailed walkthrough in the next couple slides. I'm going to mostly skip through it. But the basic goal here when you're converting your model to FP16 is to identify these non-tensor core things and make sure that they are maintaining the same principles that the tensor cores are providing, which is to keep intermediate or temporary values in high precision, and especially making sure you perform those sums, those reductions. Like when you're doing a matrix multiply, you have this big dot product and you're summing it all up into that FP32 register. You want to be doing the same thing. For example, in batch normalization, I have to compute the mean across my channels or across my batch or across whatever, and I want to make sure I compute that mean in FP32 when I'm summing up all those values, because otherwise I might lose accuracy and precision as I'm summing up into an FP16 accumulator. I have some examples. I'm going to skip through them in the interest of time, but in sort of practical recommendations, what this looks like, I'm making it sound complicated. It's actually not that hard for all of the non-exotic model architectures I've seen. You can certainly make weird architectures that are going to go outside the slide of practical recommendations. But in terms of what you want to watch out for, your nonlinearities are always going to be fine unless there's some enormous swing in dynamic range, which basically means exponentiation and logarithms. Those are really great functions to run in FP32. I encourage you to not try and do that in FP16. You'll easily blow out your dynamic range. The second thing to watch out for is normalization. So there's there's batch norm, and then there are a million other norms. There's your instance norm and your group norm and your layer norm, and I'm sure there are a bunch more norm papers that'll be presented this week. Like, people love to normalize things. It seems to be a good idea. It's a little frustrating from a hardware point of view, but it seems to be a good idea. And so it's totally fine, as with the tensor cores, to have your input and output be in FP16, but you want to keep those intermediate results in FP32. And often, if you're either writing a CUDA kernel yourself or using something from cuDNN, the library can do that for you. It can have a single fused kernel that takes as input and output FP16 and then does all of its internal math in registers in shared memory in FP32. But sometimes the framework makes that a little bit tricky. So if you just have a sequence of operations where, like, you're going to compute the mean yourself, you're going to divide by the mean yourself, and then you're going to have that output, you want to make sure those intermediate values are kept in high precision. And then the third thing here, and this is the one that actually comes up the most often, is loss functions. Loss functions usually do all kinds of weird stuff, even in the simple case of a cross-entropy loss. Like, you're going to have logarithms, exponentiation, and reductions, and pointwise operations all in a single thing. It is certainly possible, if you are very careful, to have some of the parts of that use FP16 as intermediate values. Because there's such a small part of the execution time of any model, I would say just do your loss function in FP32, and it'll make your life a lot easier. So that's it. And this is probably the hardest part of anything I'm going to say. So if you have more questions, please do come bug me at the end. But we're going to keep rolling. So the second thing, so that was first thing, right? Model conversion. We can move things to FP16, and then we identify the main things, again, mostly loss functions, and keep them in FP32. Second thing we call master weights for reasons that will become clear in a second. There's a bunch of text here. I'm going to ignore the text and just point to this picture at the bottom. What that number line is showing there is each of those tick marks is a single representable value in FP16. FP16 has 5 exponent bits, 10 mantissa bits, which means the relative magnitude of adjacent values is going to be 2 to the 10, or 1 over 2 to the 10. So, say I have a weight that is currently 1.5. It's a totally good number. It seems like a number that a weight might have. And I get some kind of a weight update. I've computed a gradient, I scale it by my learning rate, maybe I have a momentum, maybe I have an addigrad or an atomer or whatever. Like, I do some stuff and I get a weight gradient and I want to, or weight update rather, and I want to apply it to that weight. And that little jumpy green thing there is the weight update that I was trying to make. Well, it's possible that that weight update is much smaller than the weight value itself, which makes sense because often you're multiplying your weight update by a learning rate of like 0.01 or 0.001 or some I'm going to say 0.001 is a small number. I know there are many numbers smaller than it, but let's say it's a small number for the sake of argument. And so I'm not even going to make it to the next representable FP16 value. Like, I tried to get there, but I'm just going to snap back to where I was. And so what this can show up in practice as is if you're storing all of your weights in FP16, later on in training, well, it depends on your learning rate schedule, but often people have learning rate schedules where things are getting smaller toward the end of training. In principle, gradients should also get smaller at the end of training if you have nice convex functions. You guys have a habit of not building nice convex functions, so that's a little bit less true. But it does tend to be true that the weight update gets smaller toward the end. And so learning will stall out. You just are unable to move your weights from the values that they're at. And maybe you would want to accumulate many small values like that over many iterations, and the correct value for the weight at convergence is much closer to 2, but you're never going to be able to get there. There's a very simple solution to this, which is you just keep your weights in FP32. And that's what I mean by master weights. That the way this is going to work in practice in software, you have your weights, you store them in high precision, well, somewhat high precision, FP32 floating point. And then at the beginning of each iteration, you copy those over to your FP16 temporary values. Those are going to be used for both forward and backward. So you get all of the benefits of accelerating with tensor cores. You compute a gradient in FP16. You can convert that back to FP32 and apply it to your master weights. So the step that you're taking is always going to be some value that's representable in FP16, but you're going to accumulate it into an FP32 value. I hope that makes sense. I saw a couple nods, so I'm optimistic. The third thing is something we call loss scaling. I noticed about 20 minutes ago that my beautiful PowerPoint animation had been lost. So I'm going to make some gestures here, and you guys are going to imagine sort of amazingly well-designed PowerPoint things flying around. So the representable range of FP16 is approximately 40 powers of 2. That's not like quite right, but we're just going to pretend it's right. And what that is that kind of big, narrower blue rectangle off to the right side. And this is mostly fine. You'll notice for the weights and activations, all of those weights and activations, except for the actual hard zeros, which are those ones over there, are representable in that range. But there are some very small gradients. In particular, some of those activation gradients, this beautiful red rectangle over here, are being lost to 0 because they're smaller than the minimum representable FP16 value. On the flip side, because all of these activation gradients are really small, we have all of this unused dynamic range over here. Most gradient values are smaller than 1, and so there's a lot of numbers, again, between 1 and 65,000, and so we're not using that. So all loss scaling is, and I should say, this is actually often totally fine to lose these values to 0. If you start inspecting gradient statistics, you'll find out that we actually lose values to 0 in FP32. There's values smaller than, I guess, 2 to the minus 140 is approximately the smallest FP32 value. So we lose values there as well. Mostly it's fine, but sometimes if you're losing too many values for a not going to define term of too many, it's possible that the gradient you compute isn't kind of quite right. It points in the wrong direction, and you take a bunch of gradient steps that's not actually decreasing your loss function, and you wander off, and either results are worse, or you go to some terrible point in your parameter space, and it blows up, and it's terrible. So what we do is we call loss scaling. You just take your loss, you multiply it by some number, constant value, And then by the chain rule, this is your guys' homework, is to convince yourself that by the chain rule, all of your gradients are going to be scaled up by that same constant value, which is equivalent to, you can imagine now, more fun PowerPoint animations where this value here is getting dragged to the right. And so now I'm recovering all of those values that I had previously lost to 0. And then when I'm going and making my weight update, I can unscale the gradient back by that value s. So there's a question that people love to ask right now, which is how do you choose s? Because the thing that everyone would not want is another hyperparameter to have to tune. It's already like basically the worst thing. The good news is we have a simple algorithm for automatically choosing s, which I call automatic loss scaling for reasons that I hope are obvious. I'm not going to kind of go through the details, again, for the interest of time. I've got a little less than 5 minutes here. So I can give you the intuition. If anyone's worked on networking, it's the same as TCP, which is just try and hit your head against the wall, and once you've hit your head against the wall, stop. So you start with a very large loss scaling factor, and every time you see an inf or a nan value in the gradient, you know that your loss scale was too high. You overflowed during backprop, and so you should decrease the scale. Also, I should say you have to skip the update at that point because you have a bunch of inf and nan values in your gradient, and it would be a bad idea to use those in your weight update. And then conversely, if it's been a long time, for some value of long time, since you've seen any overflows, then you think maybe the scale of gradients does tend to kind of drift over time. And so at that point, you can infer the scale of the gradients has drifted down, and so you want to compensate by moving the loss scale up. I have a link here that describes it in detail. There are obviously some hyper parameters in this particular algorithm about how you're moving that loss scale up and down and when you're shifting down and when you're shifting up. We've have values that have worked on every model we've tried. I should say as a general concept, this is actually not a hard problem, loss scaling. Like, this is not learning rate tuning. Almost any reasonable thing you can think up for doing this will work fine. It's just you have to do something. Almost anything will work, but you do have to do something. We have something that works. It's available in most of the major frameworks. I have a link there. So that's it. 2.5 things, 3 things. We have model conversion. We have loss scaling, and we have master weights, kind of safe updates. Great. I have 2.5 minutes left, so we're going to just fly here. What's up? Okay. Carrie thinks we have more than 2.5 minutes, maybe 3.5 minutes. So I have a bunch of slides here walking through kind of how you might go about doing this in some popular frameworks. We definitely don't have time for this. Just a couple guidelines when doing mixed precision. Some of these are actually no longer true based on updates to cuDNN, which is great. So that having been said, if you want to make the best use of your tensor cores, it's sometimes important, decreasingly important, but sometimes important that things have the right dimensions to match the particular hardware constraints for the tensor cores. For matrix multiply, that means that each of your 3 dimensions, the kind of mn and k for your 2 matrices, should all be multiples of 8. For convolution, historically, it was important that the number of channels for the input and the output both be a multiple of 8. Is that true, Ujjwal, that no longer has to be true?
So yeah, it'll do some automatic padding.
So it'll automatically pad it for you, sometimes, probably. So check, I guess is the point. I think over time it will be true that these things are no longer constraints, but for often pretty complicated software reasons, it's often easier to just change your model, like just make it a multiple of 8. It's not that hard. The last question, and I think actually Carrie's going to say something about this, is a question that I get a lot, even from people in NVIDIA, is am I using tensor cores for my FP16 model? This historically has been kind of a weirdly difficult question to answer. I think there are better answers than the one I have. My favorite answer is use NVProf and take a look at the names of the kernels that are being invoked. And if you see the letter S followed by some digits in the kernel name, that means it's a tensor core kernel. We're not going to go through kernel naming conventions right now. I can assure you it's really boring. However, that will, for both Volta and Turing, tell you with certainty whether or not you're using tensor cores. Right, and they're much better tooling improvements, which I think Carrie's going to speak about. So you don't have to use NVProf, but if you like NVProf like me and you spend your life using NVProf, this is a great thing to do. What did I have here? Okay, I think, well, the last thing I'm going to say here is a little note about debugging mixed precision. There's a phenomenon that I like to call the unreasonable effectiveness of gradient descent, which is that you can have lots of bugs in your code, and it will probably still work. You will probably still have a gradient that's wrong, your loss is wrong, and gradient descent says, that's fine, I'm just gonna minimize the thing you gave me, and you're gonna get something that kind of works. This is really upsetting, I should say. All the chuckles seem to indicate that people have had this experience as well. So my main recommendation, maybe more than anything else when using mixed precision, is just follow some good software engineering practices, especially around testing. It's pretty easy to make some simple mistakes like not unscaling and scaling the gradients correctly, having your gradient clipping be applied to the scaled gradients rather than the unscaled ones, having weird synchronization issues between your master weights and your FP16 copies of the weights, especially in the presence of multi-GPU training. Just watch out for those things. We're gonna just skip through all of this example. I hope, will these slides be shared? I hope the slides will be somewhere. We'll definitely make sure the slides are somewhere. I have links to examples here and resources. And that brings us to the conclusion. So popping up 3 or 4 levels at this point. What I want everyone to take away is like mixed precision training. It is a general purpose approach for matching the accuracy in the machine learning sense of FP32 training while getting both memory and math savings and being able to take advantage of tensor cores. Their pretty significant speedups are really common at this point and still getting better with every new software release. So make sure your software is up to date too. That's another really good piece of advice. There is a specific methodology to mixed precision training. Like I said, there are kind of 2 things. One is this model conversion step, and the other is safe updates with master weights and loss scaling. There are a lot of tools that make it easier to use mixed precision. I mentioned one called AMP, Automatic Mixed Precision for PyTorch. There are a bunch of great tools for TensorFlow that Boris is going to speak about, so I'm not going to talk about that now. And so this is something where you can have a lot of fine-grained control if you want, or you can go to find tools to do this all automatically for you. And that is the end. Thank you so much.
That's your back.
That's my backup.
Introduce yourself.
Hi, I'm Boris Ginsburg, and I will present today OpenSeek2Seek. This is a speech and NLP toolkit that we developed for TensorFlow. This work was done with all our group and with many interns that participated in writing model and tuning them. So OpenSeek2Seek is a TensorFlow toolkit that's based on sequence-to-sequence paradigm. And we developed it with 3 major goals. It's modular design and ease of use, fast training, including mixed precision training, and scalable training for multi-GPU and multi-node setups. So we have large list of state-of-the-art models for speech recognition. Jasper, I will tell you more about this model. Deep Speech 2, wave-to-letter, speech commands, generation of speech, speech-to-text, Tachatron, WaveNet, translation, transformer, FairSeek, GNMT, language model, and more. So why we built OpenSeek2Seek? The project started in January this year as a research platform, and the goal was to build a TensorFlow platform with ease, which would be easy to use with modular design. We also wanted fast training, but by all these reasons, essentially we added float 16 to TensorFlow, our recipe for float 16 training, and we added Haravot to improve Uber Haravot library to improve multi-GPU scaling. So basically OpenSeek2Seek based on encoder-decoder paradigm, so you have to define your a model as encoder and decoder, data layer, loss functions, and we found that this approach is generic enough to support all use cases that we wanted to check. So let's skip this. So essentially, you have to describe your encoder, all parameters, and decoder, choose loss function, write data layer, and then describe how do you want to train the model. So we implemented mixed precision training following the recipe which Carl presented just a few minutes ago with a second copy of weights. So essentially all training forward, backward pass is done in float 16 weights, activation, and gradients. And before we do weight update, we convert gradient to regular float, use your favorite optimizer to update weights, and then convert weights back to float 16. So we also added loss scaling with automatic backoff, and we use layer-wise automatic rate control to speed up training and stabilize initial stage of training instead of gradient clipping. So we also added one of the problems with float 16 is that you also should modify your regularizer by the same reason why you should modify your optimizer. So we added a regularizer wrapper in TensorFlow to bypass this problem. The basic idea was that essentially we disable standard TensorFlow regularization and do it manually during optimizer stage. So instead of a standard tower-based approach, which is based on standard TensorFlow approach, we added Horovod-based approach, which is based on nickel for fast inter-GPU communications. And we found that it scales much better than standard TensorFlow approach. So, and then we developed a large set of models in OpenC2SIG for our research. So we have, as I said, translation model, speech recognition, speech synthesis, and text-to-speech models. All models have been trained with mixed precision. So it's large number of recipes that you can use for your own development. So I will talk now more about speech recognition models. Currently we support 3 models. Standard Deep Speech 2 model, very similar to what Baidu described in original paper. Wave-to-letter Plus, which is based on Facebook wave-to-letter, and our own model that we call Jasper. So numbers that we have is numbers on Libri speech word array with beam search using standard OpenSLR language models. So this is very close to published numbers in the paper. Our Jasper model is better than published Baidu or Facebook numbers. It's very close to open source best results that we have. It's still not as good as Capio speech recognition model, which was probably trained with large proprietary data set. Our model was trained only with Libri speech. I will give you more details about this model now. So Deep Speech 2 is original Baidu model with a couple of convolutional layers and then large stack of bidirectional, unidirectional RNNs, and then one follow-up raw convolutional layer and standard CTC loss in the end. So we use this model as a baseline for us. So we slightly modified to support cuDNN RNN layers just to make training faster and to use float 16. So wave-to-letter is completely convolutional layer. There is no RNN. It's pure time delay neural network with 1D convolutional layers. It's relatively shallow. This is all layers that you can see on the slide. So, and we did a few modifications. We removed two first layers because we just use standard spectrogram as input for the layer. And then added a few additional modifications. So original wave-to-letter has gated linear units, weight normalization, and gradient clipping, and their own version of CTC loss. What we did, we replaced it with few modifications. So first of all, we use stranded convolution as the first layer just to make training faster. We also have dilation in the last layer to have the same context for speech recognition as in original wave-to-letters. We replaced this model with we replaced Bayes norm with standard Bayes norm. We removed gated linear unit and just used standard rectified linear unit, and we used standard CTC loss. And we used Lark instead of gradient clipping, and we found that this model actually trained amazingly good, at least as good as original wave-to-letter, but much faster. So all this training was done on one server with 8 GPUs, mixed precision for 200 epochs using standard, and numbers are received with Bayes beam search with 4-gram OpenSLR language model. Still, numbers have been fine, but still below what we wanted. So, but we used cuDNN, and we found that using mixed precision with cuDNN tricks give us like really nice 3x speed up depending on the batch size. Between 3.2 and 3.6 speed up. So let's talk about Jasper. So we started from this model, and we decided to make it deeper, which is standard deep learning approach. So we took the whole central block and replaced it with scalable large number of blocks. We added residual connections. So now we have very deep residual 1D convolutional network. So we have, in our model, we have 10 blocks, and each block has 5 internal convolutional inside, plus 1 large residual connections that let you train much faster for such deep networks. So each block is standard 1D convolution, Bayes norm, ReLU, and dropout on top of it. The last block has a special projection to match dimension of channel of input the block and output the block. So using this very deep model already give us very huge improvement in accuracy. So we improve accuracy almost by 5% in word error rate on test others. What we found that it was much better than our original plan, but still below our target, which was go below 4% on test clean and below 14 on test others. So it's very large model, so how to prevent overfitting? We use standard speech data augmentation, and we use dropout And these are best numbers that we get using standard data augmentations. So the next idea was let's use synthetic speech to train this model. So we have a text-to-speech engine in OpenSeek2Seek, which is based on Tahatron 2 and WaveNet. So we use this text-to-speech engine to generate synthetic speech. Essentially, we took LibriSpeech text and just generated a large data set using these original LibriSpeech texts. Then we mixed this synthetic speech with original LibriSpeech half-half and retrained our model. And we get really nice improvement in both test clean and test other. This is greedy decoder, and when we use language model with beam search, we get our our original goals go below 4 and go below 14 for test others. Just to make things clear, this is evaluation loss when you train on original LibriSpeech, and you can see very clearly how overfit happens, and this is using with synthetic speech. What is interesting is that in spite of this overfit in evaluation loss, word error rate still going down for both original data set and for synthetic speech. So, and this is the improvement that we get with synthetic speech. So our next plan would be to generate much larger synthetic data sets and overcome, and data sets are one of the major problems that we have in speech recognition. Usually people use very large proprietary data set, which very difficult to get. And we believe that synthetic speech can give us the same breakthrough in speech recognition as we have in image classification or image analytics. As I said, OpenSeek2Seek is TensorFlow-based toolkit which support out-of-the-box distributed mixed precision. We have many state-of-the-art models. Like this month, we're adding speech commands to this toolkit. Contributions are welcome. We have a lot of external people who participate in this project. And these are links to the model and documentations. Questions?
Yes. How many hours of data set for speech recognition have you generated?
We generated 3x larger than original LibriSpeech, but we mixed it in 50-50 proportion. We found that if you're using too much synthetic speech, that result not as good as using, we changed the distribution of speech. Okay, thanks. And we have more 5 minutes for coffee and breaks.